Thank you very much indeed, Stephen, and thank you to you all for the invitation to speak tonight. I'll just launch the screen share if I may, and someone, if they would kindly let me know when it's working, I will begin the talk.
That's it.
Okay, thank you. So what I hope to do this evening is just give you a little flavour of some of the work I'm linked to through the Durham Energy Institute, and in particular, the future of geoenergy within the energy transition. As a geologist, clearly I believe very strongly that our future lies working in harmony with the earth, and perhaps that's not always been the case. But just to, I think it's already been done by Stephen, so I won't dwell on it too much, but I've been around for a long time. And there is a reasonably neat picture of a neat beard and neat hair of me. I worked 28 years in the petroleum industry, started my life up in Aberdeen, and that did include a number of trips up to the Shetlands, including the Great Shetland Relay back in 1984. And I think we came fourth or fifth and beat the police, which I'm not sure I could manage anymore, not with Perez on my tail, but there we go. And then I moved to, I suppose, a realization in some ways that we needed to tidy up our act somewhat. And that coincided with the move to academia some 14 years ago. You can summarize the career if you like: 28 years getting carbon out of the ground and 14 trying to shove it back in again. But let me take you on a bit of a journey. When you think about the way in which humans have used energy, you're reminded of things like the Industrial Revolution, when men in top hats, and it was virtually exclusively men, invented phenomenal machines which made at least their life a bit easier, if not for all the workers. But I was always curious about what was the driver for the Industrial Revolution. And in delving into that, particularly with regard to Durham, it turns out to be, it wasn't necessarily those guys in the top hats and big boats and steam engines that created the Industrial Revolution, but the very fact that in England, at least, we denuded our landscape of trees, and the supply chains weren't as well developed as they are today. We couldn't import wood pellets from virgin forests in Canada to burn in our stoves, and therefore folk were starving. And indeed, that was the driver for, if you will, the development of the Industrial Revolution. People did what the church had forbade them and went underground and dug some coal out. And the key thing about coal is that it's very energy dense. Yes, it's dangerous to mine, but you get a lot more bang for your buck with coal than you do with wood or wind or flowing water. And so that led to the development, particularly of the great Durham and Northumberland coalfields. And because coal could be mined and shipped along the west to east rivers, and then onto boats and down to London, the first global city, London, was built on the back of coal mined in the northeast. Much more difficult to shift it from Wales or the Midlands. The picture on the left, I happen to live in New Brancepeth, in a piece of land which was once owned by the rather draconian mine owner in the area. But along with all the districts mining around in the northeast of England was the Durham Miners Association, which actually built the city centre in Durham. And this is the only parliament, until the one at Holyrood opened, the only parliament in Britain outside London for many a year. But it was that coal mined in the UK, whether it's in the Midland Valley of Scotland or even the little bits up on the coast of Brora, as well as the South Wales and all the English coal fields, which built, I would say, along with Scottish missionaries, built the empire, whether that's good or bad. But that was the, if you like, the driving force. And we can see the correlation, if not necessarily precise cause between the quantity of coal mined in the UK and, if you like, the size of the empire. We peaked at around 1911 when some 300 million tons were mined. If we stand back and look at the bigger picture for a few minutes, this is what's happened to global energy use over, well, since the middle part of the 19th century. Initially coal, and that was added to by the time we came to the beginning of the 20th century, oil, and more recently, of course, associated gas from the coals and oil, with a little bit of nuclear and a constant theme of minor but significant hydro. You can actually, let's move away from energy for a minute and just look at global population. The global population today is around about, well, it's just past 8 billion or so, and it's likely to top out at the end of this century at around about 11. We've already seen a major change last year in that India became the largest country by population, overtaking China. And that's the same segment of time that we looked at with the energy profile, and the two overlay rather nicely. So if you like, the huge energy demand globally is really a function of the number of people. Now, of course, it's not all equitable. And if we look at how that energy is distributed globally, with some of these delightful maps, which you can pick up on the internet, the size of the country is a reflection of the amount of energy consumed. This is a couple of years ago. I didn't manage to find an up-to-date one. You can see here what we already know, that Europe, parts of Asia, particularly Japan and now China, and the US are big consumers of energy. And that has a consequence today, since nearly all the energy use is from fossil fuels, in the amount of carbon dioxide released into the atmosphere. And again, a similar map, this time on emissions to the atmosphere. Again, the emphasis is on Europe, China, Japan, the USA, and so on. How much carbon? The next graph is quite a complex one, but I only want you to look at the stuff in, oh, it's not in the red box, the stuff that's written in red, if you like. What I tried to do here, and you can argue with this somewhat if you like, but it's within a sort of geological approximation, correct? We are using, as a species, around about 100,000 years worth of accumulated carbon each year over the eons, over the millennia, over the billions of years that the Earth existed, packing away carbon. We wanted a very carbon dioxide rich atmosphere, and progressively through both precipitation of things like limestone, which is driven by animals, of course, and plants, and the accumulation of organic matter at the base of lakes and seas, the Earth has been packing away all this carbon, but we are getting it out rather quickly. And there are consequences to that, as we now understand. In the last 40 years or so, the recognition that CO2, well, it's been recognized as a greenhouse gas since the 19th century, but the impact has been recognized only in the last 40 or so years. It's impacting not just the atmosphere, which we hear about almost daily now on the news, but also the hydrosphere, the acidification of the ocean. And we're pretty close to the tipping point at which skeletal matter will not accumulate. We're also, and the fossil record is not great, of course, but the estimation is that today around about 10 or 100 times faster extinction is occurring than any time we can measure in the geological past. The geosphere gets away pretty lightly. We do have subsidence and elevation caused by humans, and in some instances induced seismicity. So let's have a look at how much energy we use. And I pull a lot of data from a couple of sources. One particularly good source is the annual review of energy statistics by BP. It's been running for about since the 1960s. Unfortunately, I would say it's got less good in recent years, and is now been either bought or passed over to the Energy Institute. We'll see how they maintain it. And this is the last year that the Energy Outlook was done for BP in 2022. I've not updated it for 2023, which will be the data out very, very soon indeed. So this was a picture in 2019, whether it's oil in green, gas in red, and so on. And that little sliver of lilac is the use of hydrogen. If we are to meet net zero by 2050, we will need to use less, but progressively more and more electricity, less oil and gas. The electricity needs to be generated from non-carbon sources, renewable sources, and the amount of hydrogen we use will also go up. The other two figures on this particular graph are just worth considering. The new momentum is not some reflection of Jeremy Corbyn's time as Labour Party leader, but rather how BP would project the data given, or the Energy Institute now, given the performance in recent years, which is clearly not very good. And the accelerated piece is, if you like, halfway between the new momentum and the net zero requirement. And of course, if we break down now we look at a normal chart of world energy use, just where the energy is going. And of course, China is using copious amounts, as indeed are the US, India, and so on. And these days, the UK no longer gets in the top 10. I think it's somewhere between 15 and 20. It's worth just looking at some of the detail in there. The US in pale blue, I'm sorry, these are all going to be in blue. It's a database I've not been able to get past and use different colors. But the US is actually diminishing in the amount of energy it uses, and China increasing, something we'd have known anyway. And you start to ask questions of what's happening elsewhere. And again, I'm not sure you can make much out of Russia here. It's up and down all over the place. Almost certainly reporting is a bit weird. But India is growing in use of energy, and Japan's on a roll down. And again, just bringing that a bit closer to home with Germany. Germany, a massive user of energy, fraction of USA, but again, it's using less. South Korea, a developing country, and Iran, which we hear lots about, but usually for the wrong reasons, also growing in energy consumption. And it's easy to start thinking, oh, the West and North America has gotten over its demand for energy and is reducing, becoming more efficient. Well, there's a little bit of that tucked in there, but as most of you'll realize, what's happened is that we in the UK, Europe, and the US have offshored our carbon emissions or our energy use by having goods built, manufactured in be it India or China or wherever. So the picture is very much complicated by the world trade and the way it's done. So how are we doing on emissions? This was the picture in 2020 or 2019. Over the years since I moved from the petroleum industry into academia, we've added another 5 gigatons or so of carbon dioxide going into the atmosphere annually. And these are the projections. There is the beginnings of the sign, largely driven by the impact of poor quality air on people's health, that at least some of the major countries are beginning to turn this over and emit rather less carbon dioxide. How are we doing in the UK? Well, it looks absolutely marvellous, but a lot of this decline in emissions, and we're now at 350 or 60 million tonnes per annum in the UK. A lot of this decline is a function of not manufacturing stuff, and the decline particularly of Teesside, which was the major industrial heart of the whole of the UK, is contributing to this apparent real emissions reduction. Some of it, of course, does come from our development of offshore wind, something which I would say is an artifact of the rush for gas in the 1980s and 1990s. So moving on to what an energy transition means. It means really not putting all that carbon dioxide or other greenhouse gases into the atmosphere, really using less. There are some methods which allow you to take carbon dioxide out of the atmosphere. Of course, we can do what we've always done, plant stuff. And in this regard, things like the peat on Shetland will be particularly important. It takes in carbon or emits carbon much faster than your giant redwoods or any hardwood plantation. There are now devices which capture the CO2 directly from air. They look remarkably like trees, bizarrely enough. And one thing which has been touted a great deal is bioenergy coupled with carbon capture and storage. The idea being that if you grow things, they will take in CO2 from the atmosphere, and when you burn them, you'll capture the CO2 and bury it. Of course, there's been a bit of cheating around on this, and it's very difficult to police. It's even many would say it's been set up badly, because you can count the full impact of a tree based upon the seedling you plant. Why is this so difficult? Well, to answer that, you really need to look at the energy density. Burning wood gives you around about 60 megajoules per kilogram. You can double that by the time you get to, or more than double it, by the time you get to petroleum or methane. And the things we're trying to replace it with, things like lithium batteries, really don't have much punch in their packet, as it were, which is clearly why we have aeroplanes that fly on liquid fuel rather than the few diddy ones which are now flying on battery power. Right at the top of that graph, uranium and thorium. Of course, that's not accessible to most people, and indeed, humans have only really built uranium-based power stations, not done thorium, despite it being about 10 times more abundant in the crust than uranium. But you can't make bombs out of the residue from a thorium reactor. The one I've not mentioned looks very promising, hydrogen. And I'll come back to hydrogen a number of times in the course of this talk, but it does have a very high energy density per kilogram. Unfortunately, of course, a kilogram of hydrogen occupies a very great volume at standard temperature and pressure on the Earth's surface, because 22.4 liters or 1 mole of methane is, I think, 16 grams, and of hydrogen only 2. So it's 8 times the volume, if you like, is 8 times greater for hydrogen than it is for methane for a given calorific value. Can we make the net zero? Well, some very, very bright people say we can, but it requires policy, investment, and an awful lot of commitment financially from governments around the world. So where are we? What have we got operating for us in globally at the moment, which is on the right track, as it were? Whether it be wind or solar thermal, all of these require materials. All of these require materials, which some of which are in short supply or themselves create environmental issues. But this was the picture last year, with total energy around about 14%. A lot of that is hydropower. So there's a lot of talk of the circular economy. If we're talking about materials, yes, we can recycle copper. Yes, we can recycle things like the rare earths, which you use in the magnets for wind turbines. Some things are very difficult to recycle, like the blades of turbines, and indeed some of the composite materials used in things like photovoltaics. But energy, no, it's forbidden by the second law of thermodynamics, but we can make much better use of what we've got. And for example, if you take a gas-fired or a coal-fired power station, it's only about 50% efficient. That means half of the energy that's in the oil or the gas or the coal which you're burning goes out the chimney. A few years ago, the British government decided to everybody would have electric radiators, quite apart from the catastrophic impact that would have had on the grid. it would have increased our emissions as a nation twofold because of the way we generate power, much of which is still through burning gas and to a lesser extent coal. So how do we displace fossil fuels? I particularly like the diagram on the right, and I'll come back to that in a minute, but basically we need to use less. You know, I moved to live in Norway with the family back in the 1980s, and we moved into a house with triple glazed windows. And that was on the coast in Stavanger, which is no colder than Durham, or I guess probably less cold given the wind in Shetland. We need to waste less, and we're incredibly profligate. If you think about a rather extreme example, an old steam engine, I love steam engines, but only about 5% of that energy is converted into power that moves the locomotive and the train. We need to develop more wind and more develop tidal, which has still been, there's only ever been Cranford Lock in Northern Ireland, where we've had a decent sized tidal system. We need to harvest the solar heat. There's a phenomenal amount of heat. Here in Durham on a summer's day, the roof temperature for our solar panels, solar thermal that is, can be about 120 degrees. Unfortunately, I can only store 2 big tanks worth of water. But we can add in geothermal, come back to that in a minute, hydrogen and possibly thorium fusion, fission rather. And I've left fusion in orange because, you know, as a little boy, I would watch Tomorrow's World, and Raymond Baxter and James Burke would say, in 20 years, young man, we'll have fusion energy. And when I arrived, I spoke to our professor of fusion containment and asked him when would we have fusion operative. He said, in 20 years, John. And a lot of times elapsed between now and then, as it were. Geothermal is a big one for me, and one of the really neat things about geothermal is this idea that you can keep using, and it doesn't have to be geothermal, it could be waste heat, but let's just say you've got a nice friendly volcano, you produce steam at 200 degrees centigrade from which you can generate power. The leftover from that is still bloody hot water or hot vapor, and that could be used for crop drying. Once you've taken that out, you could use it for food processing. It could go into your house next step, or into a greenhouse, and eventually to a fish farm, by which time you've taken maybe 180 degrees out of that water system. You keep using and reusing that system. And, you know, in many ways, it's no different from, what would it be? At least 3 generations ago, folk would sleep with their animals. They'd use the body heat to keep the whole house warm. So one of the things we do need more of is more electricity. This is again from the BP charts with the new momentum. But if you get to know, promote that electricity performance more. I'm going to take a slight deviation now, because 2022 we had some rather strange, well, they've been repeated just recently by the government as well. But in order to meet the need for more electricity, we were going to burn more coal, gas and oil and install more low carbon capacity. Very good. That was translated, and this was May 22, so a little out of date now, but it shows the cluttered thinking. Cluttered? That's the wrong word. We'll just leave it at thinking of those who are there to provide us with energy systems, that we're going to further utilise the North Sea reserves. We'll have another look at shale gas. We'll add some CCS, and we'll reduce gas consumption. Now, these are my takes in red on those. We could further develop the North Sea with much decreased emissions. Jim and I worked on a project, 15 years ago now, that would have seen a low reduction in the emissions associated with the platform use by about 50% by using co-produced water. I'll show you a graph in a minute or two. We don't have anything worth exploiting for shale gas in the UK, and that was shown more than a decade ago. New CCS, there are 2 clusters on their way now, which we'll show in a minute or two, but adding that would only give you about 10 megatons per year, and we're liberating some over 300 million tons. And yeah, we might be able to reduce gas consumption. Would be a very good thing given what's happened since 2022, but there was no word as to how that might happen. And when we're doing all this, we've got to make damn certain that we have the minimum impact on biodiversity. And indeed, there are things that we may be able to do which would increase that biodiversity. I jumped on a bit quick then, but let's do so anyway. Whoops. So I will talk a little bit about geothermal and solar thermal, hydrogen, and how to take some of that carbon out of the system. Everywhere is hot beneath the ground. It may only increase by 15 degrees per kilometre in the South Caspian, and maybe as much as 200 degrees per kilometre if you're in Iceland, but wherever you go underground, it gets warmer. The UK is middle, as it were. Typical geothermal gradients in the UK are between 25, and if you're lucky, like in the northeast or Cornwall, it's about 35 to 40 degrees per kilometre. And if we were to exploit that heat in the subsurface, even without putting cold water in the ground to get heated up again, we've got about 100 years supply or so. I've only got a map for England. There's a very good Scottish database. This database for England has since disappeared, but broadly speaking, the availability of heat, whether it's in flooded coal mines, which I'll come to, or deep sedimentary basins, more or less matches the population distribution in England and indeed in Scotland. There's only one major population centre in the UK that doesn't have a very ready source access to substantial heat, and that is London. And there's a lot of hot air in London, and I mean that in a quite literal sense. Extraction of heat from the tube lines in what is a heat island, given all the energy used in London, it's perfectly possible to make London go, or at least Westminster, go carbon neutral for heating. Some great work done by a Chinese student a couple of years ago when she was doing a PhD in Cambridge. But let's start simple. We know we've got around about 23,000 mines, all of which are nearly all of which are abandoned in the UK, most of which are coal, and they are full of water because water is flooded back in as the pumping has ceased. That water is now at the same temperature as the rock, and we've already started systems, including the one here at Manchester Wines, plus 6 megawatts in Gateshead, where water is being abstracted from the mines. 3 or 4 degrees is being taken out, and that's being used in municipal buildings, or in this particular UK's largest warehouse. The modelling work for these mines, you can see on the left a mine map with the various galleries, and that's translated into a MATLAB code, so we can look at the transfer of heat from rock and how long and how separate your injection and production systems. Get it wrong and you'll produce coal water. But again, we're starting to match history with these in the same way that you might do for a petroleum field. And these are some of the systems which are being developed in the northeast. It's an idea generated by a good friend of mine who moved from Durham University to the Coal Authority and is just coming back to run the National Geothermal Centre, which we've helped set up in the last couple of months. So deep geothermal energy, whether you've got Caledonian or younger granites, or shallow systems in the shallower systems in things like the Wessex Basin or the Cheshire Basin, Staymore Trough in Northumberland, lots of opportunities for winning warm water. But it doesn't need just to be water. This is a nice piece of work done by 2 undergraduates. I employed one summer looking at the waste heat produced in the UK. Now, it's based upon what data companies were prepared to share with us. So to some extent, the energy wasted in the Grampian region is as much a reflection of the willingness of companies operating there to share that data as it is absolute wasted heat. But again, a phenomenal amount of heat that can be harvested and stored in many places underground. And that's my take on assimilating or accumulating all the subsurface aquifers, including Hoy, in which you might be able to store heat. Coming back to the North Sea, I mentioned that produced water is of value. Every field now is getting on a bit in the North Sea, and many of those fields produce copious amounts of water, something like nearly half a million barrels of boiling water every day. And from that, you could generate about half the power requirement to push the water in the ground. And since emissions from platforms represent about 40% of Scotland's total emissions, we could start to cut that down quite dramatically. 10 years ago or more, when we did this work, no one took any interest. Today they do. So geothermal's got a lot of things going for it. Water is the key thing for moving the geothermal around. And one of the other key things about geothermal, heat doesn't move very well. And so it starts to become local. If we move on a bit to hydrogen, hydrogen is often seen as a bit of a unicorn. But the fact is, whatever pattern you look at, whether it's these accelerated or net zero, or the, if you like, goals, hydrogen is manufactured. And if you're manufacturing hydrogen, there is a cost to do that. And the hydrogen has acquired a coat of many colors in the last few years related to the process used to make it. Steam reforming is the most common, where you react steam with methane and end up emitting the CO2 into the atmosphere. Because you've had an energy transformation, doing that from a climate perspective is worse than simply burning the methane. If you capture that CO2 and bury it, you get to call it blue hydrogen. And if you electrolyze and it has to be fresh water, you get to call it green. However, there is one more that really needs a serious look, and that's the Earth produces hydrogen. We call it natural hydrogen. And if you think about it, if you're manufacturing hydrogen from, say, methane to get the grey, there'll be an additional cost to capture the CO2. Electrolysis of water is even more expensive. But if grey is made from methane, could the finding costs for natural hydrogen mimic those of methane? In which case, we should be able to bring in natural hydrogen, should it exist in large quantities, at a very low price. Now, many people in the petroleum industry are quite dismissive of the possibility of finding hydrogen, but you wouldn't tend to look where you find petroleum for the most part. Here we have some indications of hydrogen. I've just completed another rather more comprehensive chart on the right-hand side, whether it's hydrogen, methane, or nitrogen on this triangular diagram. There's lots of examples of high nitrogen containing gases. And the most famous one is in Mali. Wells were drilled for water in the 1980s, and they struck at very shallow depth, 96% pure hydrogen. It's not really hit the press, but when your security detail is the Wagner Group, that's probably a good indication as to why. What we have almost certainly in the case of the Mali discovery, which is around about 500 billion standard cubic feet, though data are very difficult to come by, is a water rock reaction. And I'll show that on the next slide. The two principal sources of hydrogen in the subsurface are serpentinization, where iron and magnesium bearing olivines react with water at temperature. This occurs in the center of the ocean spreading ridges, but of course they can't get trapped there. It also occurs in subduction areas or other areas where you're having serpentinization. And that pair reaction is driven to the right-hand side by the magnesium reaction consuming the aqueous silica generated by the iron reaction. And so you get hydrogen liberated. And that runs at a sort of rate of 1 to tens of millions of years, a rather slower process, and one I'm very familiar with because it yields helium, is the decay of uranium, thorium, and potassium, and the alpha, beta, and gamma particles in or radiation rather, when they impinge upon water, will split the water. Oxygen is mopped up by the rock very, very quickly, and hydrogen is liberated. And so there are real accumulations of hydrogen, one massive one, many other smaller ones around the world which have been found. Hydrogen, though, is very much bioavailable. You know, the black smokers have got phenomenal bacterial colonies hoovering up that hydrogen as it comes out of the vents. So you've got to devise a strategy which includes preservation as well. Finally, just to finish off the talk, tidying up. I've been associated with carbon capture and storage since I moved from academia to academia in 2009. And during that period of time, we've had multiple failures to get on with it in the UK. Probably the most disappointing was the first one. The Miller Field, which I worked on when it was discovered in 1984, came to an end a few years ago. It's a very CO2 rich gas, and it has a pipeline direct to Peterhead. It could easily be reversed, could have been, but now it's been decommissioned. So whether it's the Labour government of 2007, the coalition of 2011, or the Tory government of 2015, have all found reasons, not very good reasons, to cancel projects. Fortunately, in the run-up to COP26, we crossed the Rubicon, and we should see CO2 going in the ground late 2026 and maybe 2027, both in Liverpool Bay, going into the old gas fields and into a major aquifer in a dome shape called Endurance in the southern North Sea. And here they are. Indeed, and I won't discuss it in any detail, there are phenomenal opportunities for enhanced oil recovery, at carbon neutral, enhanced gas recovery from CO2 injection, and in a couple of instances, the possibility of, in some of the deeper fields, producing a CO2 power station in which CO2 is continuously cycled. Unlike water, it doesn't need to be pumped into the ground, it take itself into the ground. Very low power outputs at the moment from systems like that, but they will improve. So we could flip some of our larger, hotter fields into CO2, captured CO2, wouldn't escape power stations. So we do need some resources to do this. And this touches on all the bits that are not petroleum or other geofluids like hot water. Each year, institutions like the Royal Society of Chemistry or the Department of the Interior in the US publish charts on elements under threat, elements overexploited, or ones where we've got maybe 100 or 1,000 year supply. This was a snapshot from 2019, and on the right, just a different way of looking at the commodities. So a lot of the work which is going on currently is trying to use material which is less damaging to the environment. You know, particularly if you want to mine a ton of neodymium, you've got to mine 1 million tons of rock. So pretty tough. But whenever we do this, we've got to do it in linked into society. There is no use trying to do stuff when society doesn't want it. And that's not necessarily a matter of persuading society that this is good for them. Very wrong way to do things. But society will control everything that we do in the energy transition, and they need to be on board. And how much will it cost? Well, let's skip to the last slide. An awful lot. These are figures put out by the International Energy Association, and the requirements to deliver net zero in these systems by 2050 run into the trillions of pounds. But alongside this is the opportunity to develop new skills. You know, we've just mentioned the forming of the National Geothermal Centre. It will hoover up skills which have been developed over the last 50 skills and know-how 50 years or more in the petroleum industry. So there are opportunities to move things forward. In conclusion, you know, there isn't really a planet B. we've got to work with what we've got. Energy density makes that very difficult to move away from the energy dense fossil fuels. Some of the easy stuff has been done, and so the next phase of the energy transition will impact us, whether you live in cities or in the countryside, and we mustn't leave folk behind, whether they're in Shetland or Durham or Mali, and we need to do it now. As Sting said, one world is enough for all of us. Thank you.
That's very good, John. Thank you very much. There's a lot of things to inspire and concern people in there, I
Yeah,
guess.
bit of
One of
both.